Does everything else bottom blue bar? Normally that's this thing right here is normally goes here. And now
Okay. Well, good morning. I think this is the last week of the course. Today I will wrap up this initial value problem algorithms. I want to talk about two more concepts. One is what do we mean by stiff differential equations, the time scale. The other one is the idea of a multi-step method to improve the accuracy of these algorithms. And all of these ideas, of course, are synthesized into several packages in MATLAB, as well as other packages that you can download freely. So I'll take about maybe 35-40 minutes, and then we will turn on to the quiz and look at the quiz as one of the preparatory material for your final exam. There will be one question on these topics that you will find today in the quiz. Any questions before I begin? The next lecture would be the last lecture, and I don't want to introduce any new topics or new ideas. So I'm completely open to suggestion from you on how you want to handle the very last lecture. I'm talking about the Thursday's lecture. We could meet and I will just field questions, and you can say, Kumar, I didn't understand this topic, can you go over it? Or you can send me by email suggestions or areas that you want me to review. And if there aren't many questions forthcoming, then what I had in mind was I will take one of the past final exams and then just go over it as a way of preparing you and telling what I expect in the final exam. So that's what I have in mind. So if you have any specific topics that you want me to review, please do email me or come to the class with that request. Okay, either way is fine. Okay, so in the last lecture we looked at a number of important but very elementary ideas on solving ordinary differential equations of the initial value type. And we saw that we could develop that from Taylor series, or we could develop from using the Newton polynomial, as you see here. One of the problems in using the Newton forward polynomial was that you could not systematically expand the accuracy by taking more terms from the series, because you need the future values. The forward difference looks for future values. In initial value problem, you have the current value and you want to predict the future value. So if you include one step ahead the future value, then we saw that class of methods are called the implicit methods. And we saw the difference. So between the explicit and implicit, the implicit methods have the ability to look ahead any sharp changes in the solution that can occur. So they are more stable. So introduce the concept of a stability of these algorithms, and we saw that explicit methods have a stability bound, meaning you cannot pick any arbitrary step size. The scheme will simply blow up, even though the original solution to the problem is well bounded. Whereas an implicit method will remain bounded. If the original solution remains bounded, the numerical approximation introduced by the implicit scheme will also remain bounded, and that's what is called an absolutely stable system. And we saw that we could actually pair an explicit-implicit combination, the explicit method to predict an initial value, and then the implicit method to correct, because implicit method requires you to solve a set of linear algebraic equations at every time step. And so the predictor-corrector pair is a very powerful combination. And what we are going to do today is look at this idea of a stiff differential equation, which we just introduced in the last lecture. Okay, that's stability, we talked about it. So we want to develop a conceptual understanding, at least, of what are stiff differential equations, because they occur all the time in chemical systems. Typically, they occur in the form of two competing reactions. One goes slowly, the other one goes very fast. Okay, so when you have these two different time scales in any problem, the response that you get has a slow build-up and a very rapid decay or a exponential growth, and then a very slow growth again. So this is a typical example of such a system where we can actually tune the time constants. And this kind of ordinary differential equation occurs. This is from a mechanical engineering system, but as I said, chemical engineering systems have them, and electrical engineering systems have them as well. It's a second order ordinary differential equation with constant coefficients. M is a constant, which is the mass, and K is the constant, which is the spring constant, and C is a constant, C is the spring constant, and K is the dashpot constant, the constant associated with the viscous damping. And we saw as an example the door stoppers typically are, they contain both elements, a spring and a damping mechanism. And in terms of intuitive explanation, we saw that the first term is the acceleration term. This is nothing but Newton's law of motion. So the acceleration is equal to sum of the external forces, and the two external forces are the force due to the dashpot, which slows down the recovery, and the force due to the spring, which stores the energy and causes the motion to retract to its original position. Okay, so what is the solution to this problem? It's a linear differential equation with constant coefficients, right? So if you can solve this by writing the characteristic equation, of that, which will be m lambda square plus c lambda, plus k lambda plus c equal to 0. Are you familiar with this? How do you solve that differential equation? You basically propose a solution of the form that x is going to be e to the power lambda t, and take the derivative, the first derivative, second derivative, and plug it into that equation. So we are looking for a solution of this form where lambda is called the eigenvalue. Okay, and in this particular case, there will be two eigenvalues, two characteristic roots, because it's a second order equation. And by taking the second derivative, for example, d square x dt square, you will get lambda square e to the power lambda t. Every time you take a derivative, you get a lambda out of it. And that's why you get the lambda square here. M times lambda square plus k times lambda plus c equal to 0. So the two roots are, let me see. Page. Just try. Okay. Okay. So it's a quadratic equation that you can solve for. Okay. So the roots are going to be lambda is equal to minus k plus or minus square root of k square minus 4mc divided by 2m. So there are two roots, plus and minus. Okay. And what I want you to think about now is there are two roots, and if these two roots are widely different in magnitude, then we have a stiff differential equation. So under what condition will they have widely differing magnitude? Okay. And we saw in the last example that physical intuitive experiment where we said if I have two such systems on the wall, mounted on the wall with a spring and dashpot, one is with a steel ball, the other one is with a styrofoam ball. If I pull them and look at the observe the oscillations, the steel ball will oscillate and go to 0. The styrofoam ball will just snap back. So its return would be very quick. Okay, the steel ball will take a longer time. And that information is all contained in here. Yeah? So when would you get, for example, an oscillatory response? Remember, the solution to this, x is e to the power lambda 1t. There will be integration constant, another integration constant times e to the power lambda 2t. Okay, lambda 1 and lambda 2 are the two roots that come from here. If lambda is imaginary, what would e to the power an imaginary number be? Do you remember? It's a complex number. So it will be sines and cosines, and that's what gives rise to the oscillation. So if m is very large, then you'll get a negative number that is inside the square root. So that will give you the complex number. Okay, and so there will be an imaginary part that will give you the sine and cosine. Okay, I don't know whether you remember this. E to the power I theta, for example, is cos theta plus I sine theta. That's called the De Moivre's theorem. It's basically exponential of an imaginary number is given by this. So that's the way to get oscillatory response. But we are not interested in that. We are interested in the limit of m going to 0. Okay, in the limit of m going to 0, what happens to the root? For example, lambda 1. Now, if m goes to 0, there are two roots. I'm going to take the first case. If m goes to 0, I'm going to drop this term. I can do that because this is small compared to k squared. Okay, and so then as an approximation in that limit, I'm going to get this as equal to minus k plus or minus k again divided by 2m. M is small. M is not 0. We cannot divide by 0. M is small. So the second term is going to be small compared to k. Okay. Now, what happens when I get the root minus k or the plus or minus sign? I pick the minus one. Then I'm going to get minus 2k over 2m or minus k over m. That's one root. And that root is going to be very large. Why? Because m is very small. Okay. So the lambda 1 is going to be a large in magnitude. Okay. The other one, I'm not going to go through the algebra here, but what would happen if I pick plus k? In here I have plus or minus k. When I pick minus k, everything was fine. I get the root k over m, and that becomes a large number. But when I pick the plus k, I'll get 0 by 0. M is going to 0, numerator is going to 0, and denominator is going to 0, right? But the limit, what is the limit? You know how to find that limit? It's something that you must have seen in calculus. When both numerator and denominator go to 0, L'Hopital's rule, exactly. Okay, so you need to use the L'Hopital's rule because you need to find out which one goes to 0 faster. So you need to take the derivative of the numerator, including all the term, this entire term. Take the derivative of this with respect to m, take the derivative of the denominator with respect to m, and then put m equal to 0. Okay, and you will get the second root. Okay, and that will turn out to be, I think, minus c over k. So take limit using L'Hopital's rule, and you will get lambda 2 as equal to minus c over k. Doesn't have m at all in it, so its magnitude is going to remain bounded, the same number as you change m. Okay, so the solution is going to be given by x of t is equal to c1 e to the power minus ct over k plus integration constant e to the power minus kt over m. Okay, so there are, of course, two integration constants, and you need to find out the integration constants from two initial conditions. This is an initial value problem. Okay, so when you sketch this profile, suppose I will pick one of the initial condition as x at t equal to 0 is 0. Initially, the mass is at rest at initial position, and then I apply a perturbation of force, causing it to oscillate. Okay, and I want to look at the response. So if I impose that condition, then you will find that when x equal to 0, if you put t equal to 0, you're going to get from this one c1 plus c2 is equal to 0. So c1 is equal to minus c2. Okay, so you can write that solution then x of t as equal to, let me replace c1 by minus c2. So it's going to be c2 times e to the power minus kt over m minus e to the power minus ct over k. Okay, so if I sketch this solution, I'm going to get a solution that looks like this. Okay, for various values of m. So I'm going to look at the parameter. I'm going to change the mass from the styrofoam limit to the steel ball limit, and I'm going to see what would happen. So as I change m, the response is going to become like this. So in this way, m is going towards 0. As m decreases, the solution becomes much steeper and then decays like this. If I put m is equal to 0, then the solution that I will get will have a behavior that is something like this. Okay, so that is what we call the slow solution, slow part of the solution. And that is given by e to the power minus ct over k. And the fast part of the solution is this part. Very quick rise, particularly when m is small. When m is extremely small, over a very short time period, it will rise and then it will start decaying slowly. So this part of the solution is the fast. And that is e to the power minus kt over m. Because this is an analytical problem, an analytical solution is possible for this problem, we can kind of analyze it, decompose it to try to understand the slow part and the fast part. In a nonlinear problem, you cannot really do that. But whenever a nonlinear problem also exhibits such a behavior, where there is a very sharp rise and then a very slow change, you call such systems as stiff differential equations. Okay? And the explicit methods will fail typically, because to resolve the very sharp change over a very short time that is in this region, you need to take extremely small step sizes. Otherwise, the system will blow up. Because why? One of the eigenvalues is very large. Remember, the stability criterion that we saw was something like h lambda is less than 2 for the explicit method. If lambda is the eigenvalue that is very large, then h must be very small, so that h lambda is still bounded. So explicit methods are typically not good for stiff differential equations. And that's why in MATLAB you will have special algorithms for stiff differential equations, which have the subscript s appended to it, ODE 14s or 15s, things like that. Okay. So what I want you to get from this from this part of the lecture is that there are differential equations which have widely varying responses on time scales. Some respond over a fast part, the other one respond over a slow part, but they are coupled. When you have such systems, you must use special algorithms, and those are typically implicit algorithms. Okay, like ODE 15s is an example. Any questions on that? So this is just to make you kind of aware, and so the only kind of question that I will ask you would be to explain what you understand by stiff differential equations. The definition of a stiffness ratio, in fact, is lambda max divided by lambda min. The absolute value of the ratio of the largest eigenvalue to the smallest eigenvalue. So I'm going to ask you to calculate the eigenvalue for a 3x3 system, find out what the stiffness ratio is. That would simply mean you need to find the maximum eigenvalue, the minimum eigenvalue, and take the ratio. And if this number is typically greater than 100, then you would call such systems as stiff differential equations. Okay? And so you should choose a different class of algorithms. Any questions on that? And development of algorithms simply focuses our attention on implicit class of methods. Implicit methods are good for stiff differential equations, but they're time consuming because every time step requires you to solve a set of algebraic equations, whereas explicit methods are time marching, very efficient computationally. Okay, the very last idea that I want to introduce to you in initial value problem is this notion of a multi-step method. Okay. What are these? How do we develop them? And why do we develop them? Okay. So the multi-step methods are methods that require more than a single step. Imagine that this is my time axis, and at time equal to 0, and I have this differential equation dy dt equals some function of y. it is an autonomous system. Okay, so and I have some initial condition y at t equal to 0 is y0, and that is y0. So I want to predict the trajectory to this differential equation satisfying that initial condition. The trajectory may be like this. It's a continuous curve, but I'm going to be happy with finding only discrete values that are reasonably accurate, right? So a single step method simply requires the current value, and it will predict what the next future value is. Then use that as the current value and predict what the next value is, and repeat. So you just put a loop around that, and you can get the integration going for as long as you want in time domain. But a multi-step method requires more than one location before it can predict what the next one is. Why do we want, that's what a multi-step method is, okay? Why do we want to achieve that? The reason is we want to improve our accuracy. We want to control the truncation error. So the methods that we have developed, the explicit Euler method and the implicit modified Euler method, are of order of h squared and h cubed. We want to develop methods that are of order h to the power 4, h to the power 5, so that with very little additional effort, we can get very accurate result. And again, these ideas are involved in RK4, in ODE 4.5, for example. Okay, they use multi-step methods because they are very efficient. And how do we develop? That's the next question. Okay, we know what multi-step methods are. We know what we need from them. We need more data points, and we will address how do we meet that requirement of needing more data points before we can predict the next one. Question? So how do we develop them? Okay, we develop them by using Newton forward polynomials. Newton backward polynomials, because forward polynomials is what we used before, and they require future values which we don't have. So we want to use the values from the past as efficiently as possible. So if you recall the Newton backward formula, f of y is approximated by a polynomial of degree m with Tn plus alpha h. Tn is the current reference point, and alpha is my new transform variable, and h is the step size. And that formula is given by 1 plus alpha delta plus alpha times alpha plus 1 over 2 factorial delta square plus, it continues on, alpha times alpha plus 1 alpha plus 2 divided by 3 factorial delta cube at Fn plus a truncation error which is of order h to the power m plus 1. Okay, so if I take m terms in the series, the truncation error is going to be of order h to the power m plus 1. So this is the formula for the polynomial. So what I'm going to do is I'm going to substitute this in here, and I'm going to separate that equation and integrate as I did before. So I'm going to write this dy dt equals f of y as integral of dy is equal to integral of f of y dt, going from tn to tn plus 1, from yn to yn plus 1. Okay, so it's the same idea as we did before. The only difference is, instead of the Newton forward polynomial, we are using a Newton backward polynomials, so that we can take as many terms as we want in the series. And the left hand side will become yn plus 1 minus yn. Okay, that is the left hand side. And the right hand side, I need to plug in that polynomial and do the integration. Okay, and of course I need to do this transformation. T is equal to Tn plus alpha h, and hence dt is equal to h times d alpha. Okay, I need to replace that, and I need to replace that integration limits also in time. So when t equal to tn, alpha equal to 0. When t equal to tn plus 1, alpha equal to 1. And I will have 1 plus alpha delta plus alpha times alpha plus 1 over 2 factorial delta square, etc. Fn. Fn is the reference point, multiplied by dt, which becomes h d alpha. Plus, because I have that truncation error term of order h to the power m plus 1, this is going to be now of order h to the power m plus 2, because I have another h coming from there. So integration typically improves the accuracy, gives you lower truncation error. Order is more. Okay, so this allows you to now construct a whole series of formula that can, by truncating it at different levels, I can choose to truncate here or can choose to truncate there, continue this process. Because every delta, delta square, delta cube, etc., will use backward variables, numbers from the past. Okay, so that's why you have the multi-step methods, but it requires only one additional function evaluation per step, going from n to n plus 1. Okay. So this is the basic idea. I'm not going to do the algebraic details. I'll give you one formula to illustrate what a multi-step method looks like, what are the problems associated with it, and how do we overcome that. Okay. So if I truncate it, for example, with m equal to 2, okay, I want you to show this. Show you get the following. It's very simple. All you need to do is take the two terms, truncate it up to here, carry out the integration, plug in the limits between 0 and 1, and you should be able to get the following formula. Yn plus 1 equal to yn plus, let me see what the formula is. Don't remember it. H over 12 multiplied by 23 Fn minus 16 Fn minus 1 plus 5 Fn minus 2 with a truncation error of order h to the power 4. Okay, so fill in those intermediate steps and let's just discuss what this method means. How do I use it? Okay, so remember, these f's are all known, the function values at n, n minus 1, n minus 2. Because we know the function, if I know y, I can plug it in, calculate what those functions are. So what this formula requires in a conceptual way on the timeline, this is the timeline. Okay, this is 0, 1, 2, 3, 4, 5, etc. Okay, so in order to go from, for example, step 4 to step 5, if you are trying to predict n equal to 4, for example, so you are trying to predict y5. Okay, so you need y4, but you also need y3 and y2. Okay, so you also need these two values. So if you have these three values, then you can predict y5 with very good accuracy, accuracy of order h to the power 4. Okay, and then once you have y5, you can then say, I'm going to predict y6, but using the previous three values. That's why it gets the name multi-step. So every time you're taking one step ahead, you're using values from the previous values. And the formula is here. It's very easy to code. All you need to do is write that line and then put a, yeah? Oh my God. So whenever I circle it, erases. Okay, I won't circle it again. Okay, so you need three values at any instant of time with this formula to predict the next value. But you get a very accurate prediction of order h to the power 4. So what are the problems in using such a method? Do you anticipate?
How many points do you start off with?
That's the problem. How many points do you start off with? You start off with only 1 point. Because I know only this point to begin with. So I cannot use this formula at the very first step, because if I'm trying to predict y1 from this formula, it'll ask me for y0 and two values before that. I don't have that, right? So how do you overcome that? How do you think MATLAB would overcome that in that algorithm that they have for us? Yeah, so essentially use Newton forward, which means we use the method that we have already developed. The Euler method and the modified Euler method. Those are all single step methods, right? So using this, generate enough data points, and once you have enough data points, you switch to the more accurate formula so that you get high accuracy. Okay? So at what point in this particular method can you start switching? Initially, we all understand. Now I need to use a single step method to go from 0 to 1 and 1 to 2 and 2 to 3, etc. How many steps should I take before I can switch to this formula? You need to take 2 steps, right? So you need to come up to here and then here. Then when you want to go from this to y3, you will require 2, 1, and 0. You already have that. Okay, you can switch that. So that's the essential idea behind multi-step methods. And there are a whole class of these methods. Okay, and you can have explicit and implicit formulation, and you can pair them up as predictor, corrector. And the theory behind the stability analysis of this are all very well developed. So the whole course can be given on developing these algorithms. Okay, but I'm just trying to introduce you to basic ideas on ODE integrators. Any questions? You know, you're all anxious for the quiz, right? Let me ask you one last question. Now, I've kind of discussed briefly how you would develop these multi-step methods. And in this particular case, I chose a Newton backward formula using the reference point at n. Okay, so it is at Tn. And if I want to develop an implicit method using the same idea, what should I change in this particular equation? This will tell me whether you understand what implicit method is and what Newton formula does and how to put them together. Do you understand the question?
That was already implicit because you're just finding yn plus 1.
No, if you are finding yn plus 1 is what we want to solve for. That's the unknown. But if you can do that in terms of all the known quantities on the right hand side, that is yn, and then the function n, which depends on yn, the function n minus 1, which depends on yn minus 1, and n minus 2. All these are known. So this method would be called an explicit method. On the right hand side, I don't have yn plus 1. If I have yn plus 1 on the right hand side, that's what makes it an implicit. You are right. It's a different formula that you need, but it's not a central difference because central difference always has data points on both sides. Here we want marching forward. It's always going to be one-sided, weighted on one side. Okay. So here, the simplest way to introduce is change your reference point from n to n plus 1. If I construct the polynomial around the reference point n plus 1, fn plus 1, then when I expand this delta fn, delta square fn, etc., fn plus 1, I will have fn plus 1, fn minus 1. So on every term on the right hand side, fn plus 1 will be introduced, and that will make it an implicit method. That's an important idea even in the quiz. Okay, you need to pay attention to where your reference point is when you're constructing a polynomial. That's what I'm testing in the quiz. I'm asking you to construct different polynomials using different reference point, forward, backward, etc. Okay, so that will be a kind of a review for this as well. Okay, maybe I think that's a good place to stop. And remember, for next class, you come prepared with questions because I'm not going to come prepared with any questions. And,